Lecture we talked about scaling analysis. Scaling analysis is a very abstract topic in the sense, without telling you exactly a particular flow situation and what are the parameters that may influence it. Just teaching you scaling analysis in the abstract will not be very helpful. But what I'm going to do is take a detour from scaling analysis to go on to the next module, which is pipe flow. We are going to analyze pipe flow using the principles of control volume analysis that we studied before. So once we analyze pipe flow, we'll then come back to scaling analysis to see example, especially the derivation of what is famously called the Reynolds number and its role in primarily pipe flow and broadly in polar fluid mechanics. So I'm basically saying the discussion we had last lecture about how for the simple funnel problem we are taking. So if you had a funnel, we basically argued that the flow rate through the funnel depends on many parameters. It depends on the radius R2, R1, R2. It depends on the length. It depends on the curvature or angle, theta. It depends on surface finish or material. Depends on fluid properties such as viscosity, density. It depends on G. It depends on a whole lot of quantities. We need scaling analysis to identify ratios or inter ratios of input, that is, these are what I call inputs, and this is what I call output or the observable or the measured quantity. Ratios, we need scaling analysis to identify ratios of input so that the number of experiments needed to fully map a quantity, in our case example flow rate, on those that may influence it. What I mean is, if I ask you to go do a bunch of experiments varying all of these quantities, if you just count 1, 2, 3, 4, 5, 6, 7, 8, there is 8 quantities. If you even vary each of them, let's say there are 8 quantities or inputs, and let's say we vary each of them over a certain range and pick 10 values in that range. What I mean by that is, let's say we take R1. Let's say R1 can realistically be between 2 centimeters to 10 centimeters. That's 5. That's about 8. And then I have 10 values between 2 and 10 centimeters. Let's say I pick 10 values. I have 8 parameters. So 8 independent parameters time and 10 of each. So the number of combinations would be how many? If I have 10 independent quantities and I take 8 possible values of each of them, how many combinations am I looking at? 80. No. Each of them can have 10 independent values. So think of all possible combinations. That is, there are 10 values of R1 and it has to be combined with 10 values of R2, 10 values of L, theta, and so on. So how many are we looking at? 8 to the power of 10. 10 to the power 8. That is like for 10 multiplied by 10, 8 times. Or this is about 100 million combinations. Of course, we don't want to do 100 million combinations. That's not the correct thing to do. The correct thing to do is to apply scaling analysis and identify ratios. Like for example, if I choose R2 as like a parameter, instead of varying R1, R2 and L separately, I can say instead of varying R1, R2 and L separately, what I would do is vary R1 over R2 and L over R2. So I have reduced the number of variables from 3 to only 2. Might not look like a big thing, but what I just did was to go from 1000 to 100. Like trying to have fewer independent variables so that the number of combinations can be managed, can be made manageable. So these three are length quantities, so it's okay. This is an angle. This is surface finish. Usually we denote this by a quantity called roughness, which is also a length. So I can add length. I can have epsilon over R1. Sorry, R2. Okay. And then I have quantities like viscosity, density, and acceleration due to gravity. What do we do about them? If I want 4 length quantities, I'm saying I'll take one of them as a reference and reduce 4 to 3. What do I do about these other quantities which not only have length? Do you know what's the unit for viscosity? Are you asking your AI?
Look it up with Google.
The same thing these days. But anyway, if you are in the exam and you don't know the unit for something and your phone is not with you, how are we going to tackle this? How can you tell me the unit for viscosity without having to look it up but work it out?
Look at an equation for viscosity.
Okay, do you know one such equation? So what is the definition for viscosity? Can you go back to the first few lectures? How is viscosity defined? So you have a fluid, let's say you have a surface and you have fluid on that surface. And if you apply a shear stress, you develop a velocity gradient. Okay. Viscosity is the ratio between shear stress and velocity gradient. If I tell you this, or if you remember this, or if you look up this, from here, can you tell me what's the unit for viscosity? If viscosity is defined as the ratio of shear stress to a velocity gradient, now tell me what's the unit for viscosity. What's the unit for shear stress? What's the unit for stress? What is stress? Force over distributed over an area. So the unit for shear stress must be Newton per meter squared. With me? I shouldn't have to go through this, but we'll do it because I don't want you to feel lost. What is the unit for velocity gradient? Velocity gradient, du over dy, the change in velocity per distance. Meter per second divided by meter, that's per second. Thank you. So this is per second in the denominator. So if we call Newton per meter squared as Pascal, this is Pascal times seconds. So the unit for viscosity, unit of viscosity in SI is Pascal second. You shouldn't have to look up this. You should be able to derive it. Trust me, I don't remember the unit for anything, but I know the principles. I derive when I need them. Okay. So question, what are the dimensions of viscosity? So if viscosity has unit of Pascal second, can we express Pascal second in terms of only kilogram, meters and seconds, mass, length, time. Can you do that? Can you express Pascal second in terms of kilogram, meters and seconds only? You can do that. I know you're feeling maybe need coffee something. So what is Pascal? Newton per meter squared. Okay, and then we have seconds. So Pascal second is Newton per meter squared times second. And what is 1 Newton? What are the dimensions of 1 Newton? Kilogram meter per second squared. And in this mind, you would have done mass times acceleration, right? So kilogram meter per second squared divided by divided by meter squared multiplied by second, which gets me kilogram per meter per second. Or the dimensions of viscosity are mass per length per time. This is unit, this is unit, this is dimension. The reason we use, what is the utility of dimension? If you write the dimension, you can quickly switch from one unit system to another. You can go from SI to English or English to SI. You go back. Okay. Okay. So in our example today, the flow rate depends on R1, R2, length, roughness, angle, viscosity, density, and gravity. It depends on so many parameters. What we have done so far is to choose R2 as a reference length. So we can write Q depends on R1 over R2 and then L over R2 and then epsilon over R2. We'll leave theta alone and then viscosity, density, gravity. Make a note of this, okay? So I just told you the dimensions for viscosity are mass per length per time. So if I want to express viscosity divided by something else, that something else cannot only have R2, it should have some reference mass, it should also have some reference time. Because the dimensions need that. Right? You can't form viscosity with only length. To form viscosity, you need a mass, length, and time in some combination. Do you agree with me on that? You can't form a viscosity with only length. You can't form viscosity, or you cannot normalize viscosity as length or length squared or length cube, it just won't work out. Okay? With me so far? Okay. Now, for this problem, the problem being the funnel and the fluid flowing out of the funnel with the flow rate. If I ask you just in your gut, there's okay. If I ask you, or if I ask you to think about the time taken for emptying the funnel, time to empty, there is, you fill it up for that, the groups that are doing the unsteady experiment, you fill it up from that instance to the time when all the liquid has fully flown out, it will take some time, right? What is a good way to think about that time? What is the quantity that will set the time? That how quickly this thing discharges? You have your soap. Imagine two experiments. So we're so there is going to be a series of thought experiments. You have to write, you have to listen. I request people to pay attention, and watching it later on video will not help you get this. Okay, so imagine two experiments. Okay, one with soap and other with water. So tell me in which case the discharge time will be lesser and which case it will be higher in discharge. Time to empty. So between soap and water, which fluid will lead to lower discharge time?
Since water is less viscous, it would be quicker.
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 Everybody agrees with that? Water will empty out sooner. If you don't believe me, you can try it. That's the cool thing about science. You don't have to believe anyone, you can actually do. Right? And you shouldn't believe everyone. That's also the point of science. Anyway, so water will discharge quicker because what? Why? Why did you say that?
Less viscous.
Because water is less viscous. Okay. So I want a reference time. So I want to use T discharge as a reference time. Or what other quantity will determine T discharge? Like for example, I'll give you another experiment between, let's say, soap and mercury. Which do you think will fall out faster? I mean, these two have different viscosities, but they have similar densities. And between soap and mercury, which is the heavier liquid? Mercury. Heavier liquid. And why it should matter? Why this problem should have a dependence on density? Because the driving force for this flow is the weight of the fluid. If you had a fluid that's quite heavy, or if you somehow bring molten metals, that will drive a much faster flow because the metal is going to be heavier, like mercury. So I'm going to think that this discharge time depends on both viscosity and density. What's the dimension for viscosity? We just did that. Mass per length per time. What's the dimension for density? You know this from your high school. What is density? Mass per unit volume. So this is mass per unit volume is a length cube. Okay. So if I take the ratio of these two, what do I get? Viscosity divided by density. What is the dimension of this quantity?
L to the 4.
Would it be length squared per second or length squared per time? Right? If I take the ratio of these two, the mass will drop out, giving me length squared per time. With me? Okay. See, most of what I say will make sense when I say it. I tell you that. It's that you have to remember the threads so that you can still piece it together later. This one step, if you look at it, it will look like, yeah, of course that makes sense. But you have to remember the entire argument. Okay. So this is length squared over time. Okay. I already have a reference length. My reference length is, I have a reference length. And what is that? In this case, that is R2. So if I take the quantity, viscosity divided by density divided by R2 squared, what is the dimension of this quantity?
Time negative.
Time inverse, right? Time inverse. Okay, so if I want a reference time, I can make the case it should scale with rho R2 squared over viscosity. It's like saying, if I have a very heavy fluid, or if I have a very less viscous fluid, or if I have a wider tube, this reference time will be large. It scales with all three of them. Okay, so if I want to take this quantity G, express G using L reference, which is R2, and T reference, which is rho R2 squared over mu. Can you do that? Can you normalize G? That is, express G divided by something that will give you a non-dimensional ratio, or a non-dimensional ratio. Can you try that? What should you divide G by to get a non-dimensional expression or form of G? Sorry? G is what? Okay, I think since you missed the first part of the discussion, what are the dimensions of G?
L T squared, T negative 6.
The dimensions of G are length, time to the negative of second, right? So to get G, I need to combine a length with and divide that by a time squared. So I can write this L reference divided by T reference squared. That will give me a non-dimensional expression for G. Okay. What if shall we do that? That is, we'll try doing that. So G divided by L reference divided by T reference squared is going to be G divided by R2 divided by what is T reference? Rho R2 squared over mu, the whole square. So this is going to be G. Sorry.
Why is the L squared?
G divided by R2 times rho squared R2 squared over mu squared. R2. So I'm going to get rho squared R2 to the cube G over mu squared. So in my list, I'm going to write, instead of G, I look at rho squared R2 cube G over mu squared.
Aren't you supposed to flip the fraction, rho r squared over mu?
Squared. Sorry, what should I do?
You do like change flip, you keep g over r2, you change the divide to a multiply, and then you flip the last fraction, rho r2 squared over mu.
Okay, I understand this can be confusing. So let me just flip it here. So this is going to be G times T ref squared divided by L.
Oh.
Okay, we'll write it like this. So G divide L ref, G divided by R2 multiplied by what is T ref? Rho R2 squared divided by mu, which gets me rho R2 cube G divided by mu squared. See, keep remembering the point of this exercise is to turn everything into a ratio. Every independent quantity should become a ratio so that you don't have to vary each of them separately. You just vary these ratios and design your experiment. Okay. We thought of a reference length. Reference length in this case is R2. We thought of a reference time, which in this case is T reference equal to rho R2 squared divided by mu. Can we think of a reference mass? What do you think will be a good way to think of a reference mass that is relevant to this problem? Your cup is filled with that liquid. What is a reference mass that is meaningful for this problem? Should it be the mass of the funnel? Should it be mass of the fluid that is contained here? Should it be mass of the air? What is a quantity that connects with this problem or relevant for this problem? Again, think about if you started with the whole cup filled or versus only 50% of the cup filled, the mass of what actually influences the discharge time or the flow rate or velocity or anything that you care about. Fluid. Mass of the fluid contained in this cup, right? So if the mass of the fluid, so M reference should be the density of the fluid multiplied by volume of the cup. The volume of the cup depends on many things. It depends on radius, it depends on length, it depends on so many things. Instead of going for the volume, we'll just say R2 cube. Reference length cube. I'm not saying this is a mass of something concrete, but what I'm saying is if you take density times R2 cube, you are getting a reference mass which is sort of represented. Okay. Okay. So if I were to pick, or if I were to take viscosity, and viscosity is m, length, inverse, time inverse. Can I express mu, or can I non-dimensionalize mu in terms of R2 or L ref and M ref. I'll still have a time. I think I messed up with the reference time. We should have chosen something else for reference. Okay, this was a bad choice. I'll walk this back. What other time that we can think of for this problem which doesn't depend on viscosity? So you have a reference length which is R2. What other time can we choose as a reference for this problem?
Gravity.
Good idea. I shouldn't have normalized gravity. So what you are saying is, if I take G has dimensions of L, T to the minus 2, and if I choose G divided by R2, that has units of T to the minus 2. So if I write T ref equal to R2 divided by G square root, this is a good reference time, isn't it? It scales with gravity, meaning if gravity is stronger, this time will be smaller. If gravity is weaker, the other way. And this also scales with R2. So this is a better reference time than what I had before. So this is wrong. Okay. So all this is wrong. I'll rewrite this. So coming back here, reference length is R2. Reference length is R2. Reference time is square root of R2 over G. And reference mass is density times R2 cube. Okay, so now I'm back on track. What I'm going to tell you is using L ref, T ref, and M ref, express mu as a ratio. Meaning, if mu has dimensions of mass per length per time, what should I divide mu by to get something that is non-dimensional? Non-dimensional meaning mass to the power 0, length to the power 0, time to the power 0. What should I divide viscosity, or using a combination of these three to non-dimensionalized? I should be taking M ref, multiplying it with L ref inverse, multiplying it with P ref inverse, and that should non-dimensionalize viscosity. What is that quantity? Viscosity divided by rho R2 cube divided by R2 divided by what is L2? Sorry, what is time? R2 over G to the minus I. To the minus half. Okay, so this is going to be viscosity divided by rho R2 squared, or actually R2 squared times G over R2 times square root of G square root of G square root of R2 over G. So this gets me mu divided by rho R2 cube G. This quantity is unitless. So instead of now varying viscosity separately and density separately and G separately, I can write this is viscosity over density times R2 cube over G. Okay, I lost my way a little bit, but now I think I'm back. Take a pause, let me summarize it, and then I'll give you time to write this up, okay? So, sorry for the confusion. Listen up, please. This is our problem. That is, we want to study the flow rate through the funnel as a function of all the quantities that influence it. And the list we have is the upper radius, the tube radius, the length of the tube, the surface roughness of the funnel, the angle of the funnel, viscosity of the fluid, density of the fluid, and acceleration due to gravity. If you have to do experiments, and let's say you choose to vary R1 10 possible values, then you can count 1, 2, 3, 4, 5, 6, 7, 8. 10 possible values for each quantity, and each of these can be independent. So you are looking at a total of 10 power 8 combinations, which is unmanageable. So then from here, this is step one. Step one, list the parameters that can be independently varied and influence the output, in this case being Q. So this is step one, setting up the problem. This is like setting up your project problem. You are now setting aside Wednesday evening to do this experiment. Only problem is you identify there are 8 variables and you have to do 100 million experiments by April 16. Doesn't sound too difficult. Let's not do it. Then to simplify the problem, what we do is choose reference length, time, and mass to express these parameters as non-dimensional or dimensionless ratios. How we do that? Those who are like listening, how we do that? First, we have to choose the reference length and time. So we choose that here. Reference length is any length that makes sense for the problem. Meaning, we took R2, which is the radius of the or the smaller radius, and chose to express everything else as a multiple of that. It's like saying the R1 is not an independent number, but R1 is simply 5 times R2. L is simply 3 times R2, or the roughness is only 1% of R2. So everything you start measuring in terms of R2, or everything you start expressing in terms of R2. So that is reference length. And then we think of a reference time, a time frame or time scale that is logical for the problem. What is logical for this problem? What is driving the flow in this problem? If you fill the cup and then you watch it discharge, what is primarily driving the flow? First I said viscosity density, but think about it. It's gravity that's driving the flow. If you took this funnel to the International Space Station and did the same experiment there, would you have discharge? You won't have any because the gravity is not there to push it. So we choose gravity as one of the quantities, and how you do the matching? Express gravity in terms of its dimensions. You already know what the reference length is, so this is R2 multiplied by T ref to the minus 1 equal to G, which gives us T ref equal to R2 over G, R2 over G, which is what we have. Oh wait, sorry, squared, squared, squared. With me so far? Even if you miss the first part, I'm trying to say everything in one place. Okay, so I'll erase this. We got a reference length, and then for reference mass, a mass that connects with the problem. So what mass is relevant here? Should we worry about the mass of the funnel? Is it any relevant to the flow? It should be think of, I'm just giving you some false choice. Is the mass of the funnel any relevant? No. The only thing that drives the flow is how much mass of fluid that you have here. More mass means more flow or higher flow. Right? So we take M ref to be, in this case, mass of fluid contained in the cone, which should scale with density times volume of the cone. But instead of expressing volume exactly, we are just saying it should be, let's take M ref equals rho times R2 cube, because R2 is our reference length. Okay, so you get rho times R2 cube. So you have used R2, you have used density, and you have used viscosity. With me so far in the story? You're going to do this for problems that you have not, that we are not discussing here. That's going to be on the test, giving you a one page or a half page description and a list of quantities. You have to reduce them to ratios. That's how the problem solving in this unit works. Okay. What do we do about viscosity? So think about the three quantities R2, density, and G that have been used. Now what do you do is express remaining quantities, which in our case includes R1, L, epsilon, mu, and theta, in terms of R2, rho, and G, or to remember it, I always think of it as in terms of L ref, M ref, and T ref. These are nothing but combinations of R2, rho, and G. How to express R1? How to express R1 in terms of M ref, L ref, and T ref? What mean? It's a very simple question.
Right.
It would just be R1 divided by R2 because length over length. So choose A, B, C, the indices such that the ratio is unitless. How to express, let's say, L in terms of the three quantities. What's the natural choice? If I want to non-dimensionalize L, L over R2. If I want to non-dimensionalize epsilon, which is a roughness, like if you measure the roughness in millimeters or something, it's also a length. So epsilon over R2. So these three all are ratios that are dimensionless. Okay, so this is step one. This is step two, identifying the reference length. And then step three is expressing as ratios. So you have Q now depending on R1 over R2, L over R2, and epsilon over R2. From 8, we have at least come down to 3. There is still one more, but at least we have reduced it. Okay. Let's think about mu. Let's think about mu. Mu divided by m ref to the A, L ref to the B, and T ref to the C. The dimensions of these should be M0, L0, P0. So get me A, B, and C. Can you try that? It's where knowing the dimensions for viscosity is important. So what's the dimensions for viscosity? We saw that at the beginning of the class. Dimensions for viscosity are m, L to the minus 1, T to the minus 1. And then I have m ref A, L ref B, and then T ref to the C. So obviously A should be equal to 1. It should be equal to 1. B should be equal to minus 1. And C should be equal to minus 1. I'll take a break here. Those who want to catch up writing, please write up to here, and I'm going to erase this portion to make space. Okay, I'm going to erase. So some of you who arrived late, George, have you started your project? Have you had a meeting with your group mates about the projects? This Wednesday? Okay. It's coming up in 9 days. There won't be any extensions, no late submissions. If it's not there on the 16th, you'll be given 0. That is not just you, telling to everyone. Okay, so please take this seriously. Isaac, have you started the work with your group?
That's after this class.
After this class. Okay, so I'll ask again on Thursday just to make sure all of you have started something. or get, some work done. Okay.
The due date for the project is 16th.
16th. So I discussed it last Thursday, 2 weeks from last Thursday. I posted that by email. So what this means is, if I take viscosity and divide it by mref to the power 1, mref, and then multiply that with lref inverse and tref inverse, this quantity must be unitless. That's what it means, and you can check that. So if we take viscosity, what is mref? Rho times R2 cube. And what is lref? R2 to the minus 1. And what is tref? That is R2 over G to the half, and then I have to have a negative sign. So this is viscosity divided by rho R2 squared. And then I have G over R2 to the power half, or this is viscosity divided by rho times square root of R2 cube times G, or this is viscosity times rho R2 square root of G R2. Check if this ratio is unitless. Check it. Don't take my word. Let's check it. How will you check it? Viscosity has units of Pascal second. Density has units of kilograms per meter cube. And GR2 square root. What is the unit of this quantity? It is famously equal to velocity when we did Bernoulli equation. So this quantity has unit of meter per second, and R2 has units of meters. So if I put everything together, the numerator is Pascal second divided by density is kg per meter cube, R2 is meters, and then square root of GR is meter per second. So I'm going to get Pascal being Newton per meter squared, Newton being kg meter per second squared time or per meter squared times seconds divided by kg per meter per second. I did that, but you should do it on your paper and see if you agree with me. So viscosity divided by rho R2 square root of G R2 is another dimensionless ratio. So over here, I'll write mu rho R2 square root of G R2, and then I have theta. So we had 8. We have now reduced it to 5. 8, then 5. What about the angle theta? Can we express angle in terms of mass, length, and time? Can we or can we not? We can. How?
Can you do like since data is like a representation of, you can like put it with respect to L in a way?
See, you cannot express angle in terms of a length alone. Because even if you take, let's say an arc, okay, you can say L over R is theta. Okay, in this problem, you are given theta as an independent angle. If you are able to do a calculation of the cone's volume and geometry, you can in principle get it. But most of the time, an angle is something you can't express in terms of a length, time, or a mass. You just treat that as a separate dimension, separate quantity. So wherever angles appear, you just leave them because they are non-dimensional already. They are radians, but they are not considered to have a unit. Okay, so you just leave it as such. Okay, so all the lengths that were previously in the problem have now been reduced to length ratios. The two quantities rho and g are used to get reference length and reference mass. So the remaining quantity viscosity is now expressed as a ratio, and then you have angle. So here is where it actually becomes useful. If you want to measure flow rate for different liquids, it doesn't make sense for you to take every possible liquid and try it. You can try to vary this ratio because both viscosity and density and G and R2, they all influence the flow rate. Instead of varying 4 of them, you just vary this one ratio. Okay. So what else is remaining here? What about this flow rate? Can we non-dimensionalize this flow rate and turn this into a relationship between relationship where you have a non-dimensional Q and other non-dimensionless or other dimensionless ratios. How to non-dimensionalize Q? What is Q?
Well, 2 times area.
Q is flow rate, right? The dimensions of Q must be length Q per time. So how do we express Q as a ratio here? If I want Q divided by something like a reference length Q multiplied by time inverse, what will that quantity be? Q divided by R2Q multiplied by T reference, which is, what is T reference? Square root of R2 over G, but I have to invert this. R2 over G inverse. So this will be Q divided by R2Q G over R2 to the half. So this is going to be Q R2 squared times square root of GR2. So instead of Q, we can write this Q divided by R2 squared times G R2. If I'm interested in expressing flow rate, because flow rate also, if the radius were bigger or G were higher, it will vary with that. So you are trying to not capture that variation also. But if I'm not interested in flow rate, let's say I'm interested in discharge velocity. What is the good scaling for discharge velocity? You already saw that somewhere here. You just have to tell me. Instead of Q, I'm interested in V discharge. How to normalize V discharge? What is the good velocity scale over here? V discharge. I want to express this as L reference multiplied by T reference to the 1. This is V discharge divided by R2 over G to the negative half. So this is going to be Vd over square root of GR2. Square root of GR is the scaling for velocity. When you do your experiment, that is your project, and you start collecting data for flow rate or height, and you then run into plotting those quantities, think of how you would present them. Would you present it as Q over time, or would you want to present it Q non-dimensional versus T non-dimensional? Okay, we'll revisit this maybe after your project is submitted. Okay, because scaling analysis is not like a standalone topic in fluid mechanics. Every problem that you study involves several inputs and maybe even several outputs. So you'll have to think about how to present the data or how to analyze the data. Okay, we'll do some examples today. Problem 7.9, if you have your book with you. I'll pull it up here. Problem 7.9 from the text. Problem 7.9, page 390. You have the. So this scaling analysis is a topic which in the exam 3, I'll definitely ask at least one, maybe two problems, but I won't ask it in the final. It's something you keep using and you slowly absorb. It's not something that you can easily memorize or master, but practice will help. Problem 7.9. Take a read. I'll give you 5 minutes. Then you'll have to come up with a strategy and tell me what to do. I'm not going to do anything immediately, but you will tell me what to do. Problem 7.9. At a sudden contraction in a pipe, the diameter changes from D1 to D2. The pressure drop which develops across the contraction is a function of D1 and D2, as well as the velocity V in the larger pipe and the fluid density and viscosity. Use D1, V, and mu as repeating variables to determine a set of dimensionless parameters. Why would it be incorrect to include the velocity in the smaller pipe as an additional variable. Don't worry about the second question. Let's just use d1, v and mu as repeating variables to a suitable set of dimensionless parameters. We'll try to do that first. So where does the problem begin? How do you state the problem? What is the quantity that we are interested in? The output, the pressure drop, delta P. That's the quantity we want to understand, and it depends on what all quantities? D1. So if you are done making note of the details, can I pull it up and use the whiteboard? We'll solve this problem or analyze this problem. Good. Can I pull up the leave it here. Yeah, I can write here. Okay, so we are interested in understanding the dependence of delta P on D1, D2. That is, here's the problem. You have a pipe with diameter D1, and then there is an obstruction with diameter D2, and we want to know what's the pressure drop across the obstruction. So the pressure drop delta P depends on the diameters D1 and D2. It also depends on the velocity in the larger pipe. That is, when the fluid enters the larger pipe or fluid is coming through the larger pipe, we'll consider its velocity to be V. So V also influences the problem. And then fluid properties like viscosity and density also influence the problem. With me so far? Our output is delta P. Our inputs are D1, D2, V, mu, and rho. Okay. So the problem says use D1, V, and mu as repeating variables. I'll tell you what that means. Okay. What I told you is pick a reference length, which we'll pick as D1. Pick a reference time, which we'll pick as V, D1 divided by V. Why is D1 divided by V a reference time? What is the dimensions of D1? Length. What is the dimension of velocity? Length per time. So if you take the ratio, you will get a time. So we are considering that to be our reference time. Okay. And then reference mass. Now I'm going to pull this up. So the problem tells you to use viscosity, right? So I'm asking you, viscosity, what are the dimensions of viscosity? Mass per length per time. Okay. So if I write M or mu ref, per length or L ref to the minus 1 and T ref to the minus 1, this must be unitless. So, okay, all right. So from here, so that means viscosity multiplied by L ref multiplied by T ref divided by M ref must be unitless. So M ref, reference mass, should be viscosity times L ref times T ref. What is viscosity times L ref? D1. And then what is T ref? D1 over V. So I have D1 squared over V. This must be M ref. So this is mu D1 squared over V. Look at this. This involves only length. This typically involves length and a velocity. And this typically involves either viscosity or density. Viscosity or density and a length and velocity. So you have used D1, V, and mu. Now express the remaining two in terms of these three. So step one is this. You write the problem. Step two is you pick reference lengths. And then step three, express remaining quantities in terms of M ref, L ref, and T ref. Remaining quantity in this case is D2. How to express D2? How to write D2 as a ratio? D2 over L ref, good. Which is D2 over D1. Okay. Then what is the other quantity? Rho. How to express rho in terms of these three? That would be M ref times L ref cubed. So that is density over mu D1 squared over V times D1 cubed. So that would be rho D1 cube divided by mu D1 by rho V divided by mu D1 to Correct? Okay, somebody should stop. This should be density, mass,
-3.
-3, mass per unit volume. So I will have mu d1 squared over v multiplied by d1 to the -3. So I would have rho v d1 divided by mu. So if I normalize density, I'm getting rho Vd over mu or rho V d1 over mu. So that is step 3. There is still one more quantity remaining, which is delta P. That also needs to be non-dimensionalized. So I have delta P divided by m ref to the power A, L ref to the power B, and T ref to the power C to be unitless. So to get A, B, and C, write out the dimensions of delta P and match. What are the dimensions of delta P? What is delta P? It's pressure, it's normal stress, that is, it's Newton per meter squared. So it would have the same dimensions kg, meter per second squared per meter squared. So this would be mass per length divided times t to the -2. So A will be 1, B equal to -1, T equal to or C equal to -2. So delta P divided by what is reference mass? Mu d1 squared over V multiplied by what is reference length? d1 to the -1. What is reference time? d1 over V to the -2. Delta P mu d1 squared over V 1 over d1 V squared over d1 squared. So I get delta P times d1 divided by mu V. Can I erase this part? The middle part. So last step, step 4, write them as a functional relation or relationship. Meaning you had from step 1 delta P equal to a function of d1, d2, B, mu, rho. What we have now transformed is delta P multiplied by d1 divided by mu V equal to a function of d1 over d2 and sorry, D2 over D1 and rho V D1 over mu. So from 5 variables, we are down to two ratios.
Factor out G.
Oh, G is, sorry, like a function G of X, okay? So I'll say F. A different function, like the algebra can look different, that's why I want to use a different function. F meaning function of. Do you look at this ratio rho Vd over mu and do you recognize it from somewhere? So we'll continue this next lecture. This rho Vd over mu is the famous Reynolds number. And for any fluid flow problem that involves density and viscosity, Reynolds number will show up. It will always show up if the fluid has a density, which it will. And if the fluid flow is viscous, in most cases it will show up. It depends mainly on density, viscosity, which are fluid properties. It depends on the velocity, which is a flow property, and diameter, which is a geometry. So this is a fluid property. P, which is a flow property, and D1, which is about the geometry. So it's a combination of all three. And we'll see pipe flow, we'll see flow over a sphere, we'll see some examples that prove to you that Reynolds number will show up from now on every time you analyze a fluid problem, pretty much. Okay. We have 2 minutes. Quick questions on today's thing. I know your BAs have been very silent. It's a little bit abstract, but if we do 2 more examples, I'm hoping it will get better. Okay. Other questions? So everybody is committing to get starting on the project, and everybody is understanding that there won't be any extensions or late submission allowed. If I open that for one person, I'm going to get a ton of requests from this course, the other course, and everything. So no, unless there is a medical emergency involved, nobody is getting extensions. Okay, let's be very clear. Okay, so please work on the project. Report like a 1 sentence update to me by next lecture. Hey, we met. Hey, we tried. Hey, we got an initial video. We are going to fine tune it. Something. One line update from each group next lecture. Okay. Thank you. Yes.
Have you gotten a chance